Hello again, students. Okay, so we are going to move to the second section, which is the characteristics of Brønsted acids in water. Now, there are three types of acids that we will look at, especially those that contain oxygen and hydrogens. Obviously, we need the hydrogens for there to be proton donation. So the first type of acid that we're going to look at is what we call an aqua acid. Okay, this is where we have an acidic proton that is on a metal coordinated to water molecules. So if you have a look at the picture, you will see that there is a water molecule here, among many others, and it's directly coordinated onto the metal atom itself. We're going to see that there's three classes of acids, and we will find first one that we've dealt with is the aqua acid. We then get the hydroxo acid, and then finally we get the oxo acid. If we look at the hydroxo acid, here we have an acidic proton that is on a hydroxyl group without there being a neighboring oxygen group. So if we look at the diagram, you will see that this is a tellurium metal and it's coordinated to 6 OH groups. This is then obviously called a hydroxo acid. The final one that we look at is called an oxo acid, and this is where we have a Brønsted acid that has an acidic proton that is on the hydroxyl group with an oxo group attached to the same atom. So if we have a look at the picture, you will see here is the hydroxo group and this is the oxo group. Please also take note of the fact that this is sulfuric acid and it's written in a different way. It shows you that there are actually two oxo groups. Here is the two oxo groups, the sulfur, which is the central atom, and then the two hydroxo groups. Okay, and there's a specific reason why we write it in this way. You're going to see shortly. Okay, with regards to metal atoms and cations, there are two contributing factors for there being the strength of an aqua acid. The first one is that the larger the charge, the positive charge of the central metal ion, generally the stronger the acid of the complex that is going to be formed. And that's obviously because of a decrease in ionic radius. If we look at the oxo acids, this table is quite important. It has some information in it, and it also gives you the pKa value so that you have an idea of how strong these acids are. Okay, so if we have a look at this example over here, you will see that the pKa value is 7.2. If it's a large positive value, it means that it's a weak acid. Okay, here we have carbonic acid. You should recognize that, H2CO3. The pKa value is 3.6, and that's also, we know, is a weak acid, but compared to this acid here, hypochlorous acid, it's a lot stronger. If we look at nitric acid, here is nitric acid, you will see it now has a negative pKa value, which means that it is a strong acid. Okay, so there are other acids in the table which you can take a look at, and you can just see for yourself whether they are aqua acids, oxo acids, or hydroxo acids. Okay. there's some other examples on the right hand side of the slide here. So there's this example here, there's this example here, and this example here. This example at the top, this one that I'm looking at here, is called sulfamic acid. This one is phosphorus acid, and this one we know as thiosulfate anion. Now, there's a method to determining the strength of oxoacids. The strength of a series of oxoacids containing a specific central atom with a variable number of oxo and hydroxyl groups can be calculated using a method that was developed by Linus Pauling. Pauling's rules are given in the slide. Go over them slowly and you will notice something. Okay, first of all, you need to write the formula in a specific format. Now remember, I've mentioned to you that this is a special way of doing it. You need to write it with the number of oxo groups. These are the oxo groups. Okay, you need to write the central atom. Okay, and then you need to write the hydroxo groups. And you will see that there's the letter P and the letter Q over here. All right. So how do we then calculate the strength? We can use Pauling's equation that he developed. It's an approximation. It's not an exact calculation. And it says that the pKa is approximately equal to 8 minus 5p. Okay. Remember, it's P from this formula here. All right. So P is the number of oxo groups. Q is the number of hydroxyl groups. Then you can get successive pKa values for polyprotic acids where Q becomes larger than 1, and that kind of increases by 5 units for every successive proton transfer. And I need to remind you that this is just an approximate calculation. There is a very good example in the textbook that you can try, example 4.5, and you'll be able to see exactly how we calculate these pKa values to give us some idea of the strength of these acids. There are a few structural anomalies regarding acid strength. Okay, so the first one results from carbon dioxide. When carbon dioxide is is dissolved in water, it forms carbonic acid, and we know that can be written, this formula here can be written as sorry, I have to do this slowly, H2C, oops, O3. Okay, but remember we write it in the way that Pauling wants us to write it. And if we do a pKa calculation, or actually if we look up the pKa value for carbonic acid, we see that the value is 6.4. But if we do a calculation with Pauling, we find that the pKa value is around about 3. Okay, so the higher pKa value is indicating a lower acidity. Remember that a more positive pKa value means very weak acid, and a more negative pKa value means a strong acid. Alright, so the reason that we get this elevated pKa value for carbonic acid is because of the equilibrium equation that assumes that all the carbon dioxide is present as carbonic acid, which is not. We know that carbon dioxide, not all carbon dioxide can dissolve in water to form carbonic acid. And if we look at the experimental values, we actually find that only 1% of the CO2 is present as carbonic acid when this is taken into account. And the true pKa value that we can actually measure by experiment becomes 3.6, which is actually closer to the Pauling value that he predicts. So we can use Pauling's rules to detect structural anomalies, as I've said. Another example is sulfurous acid. Again, there's a structural anomaly because of the difficult equilibrium side reactions. Remember that not all non-metal oxides react fully with water. We do get anhydrous oxides. This is when we get metals that dissolve, they form usually basic oxides, and non-metals typically form acidic oxides. We need to remember that the acidic oxide is an oxide that when we dissolve it in water, it binds a water molecule and releases a proton. So very good examples would be carbon dioxide going into water to form carbonic acid, and then that carbonic acid going into water to form your hydronium ion over here and the anion. Okay, and obviously we have an equivalent interpretation that if we were to put the carbon dioxide into a solution of base, we would get the same species altogether. If we get a basic oxide, it's an oxide where a proton is transferred when it dissolves in water. So for example, if we take barium oxide in water, we form a very strong base in terms of the hydroxide anions, and we can see that if we were to react the basic oxide with water, with acid, so we'll have the basic oxide here reacting with acid, it will give us the cation and water molecules. We also get amphoteric oxides. Amphoteric oxides are ones that react with both acid and base. Aluminium oxide is a very good example of this, where it can react with acid to give us two different types of complexes. This is self-explanatory. In the periodic table, we can also see that the amphoterism can vary with oxidation state. So all the ones that are circled here, this one, these ones, etc., etc., this is where you would find the amphoteric oxides. And again, with the transition elements, it gives you an idea of, with the oxidation number, the plot of oxidation number going this way, and the type of element going this way, we see where the metals will be acidic, where they will be amphoteric, and where they will be basic. We obviously also get polyoxocompound formation. I've mentioned this briefly before in an earlier section, where some acids having hydroxide groups condense to form polyoxoanions, and they make polycations. The oxoanions can form polymers as the pH is lowered, whereas some of the aqua ions form polymers as the pH is raised. Polyoxoanions account for most of the mass of oxygen in the Earth's crust, interestingly enough. Okay, the example that you're going to be working with is polyphosphoric acid. It'll be one of the practicals that you actually do. This is the reaction that you can see what happens, and it actually is a useful thing that this thing forms polymers. It's a means to storing energy in your body. These are kind of like what the reactions look like. In this reaction here, we have two phosphate molecules reacting with acid to give us the polyphosphoric acid, and three water molecules, and this are just the structures. I will give you more information about the practical when the time is due, and we'll pick up the rest of this section in the next lecture.